So I'm Erik van Loon. I work at mathematical physics here in Lund, and I mainly work on the kind of theoretical and computational modeling of materials. And today I will talk about two-dimensional materials and electronic correlations in those materials. I do theory, but I think based on the audience, I will focus more on the results and on how the theory is done. If you have questions, please come to me during lunch. Okay. How do I go to the next slide? So two-dimensional materials are of interest, partially since the discovery of graphene, which was kind of the hallmark two-dimensional material. And since then, it has been realized that if you have a two-dimensional material, you can do lots of fun stuff with it. So if you have several of them, you can stack them together as in this heterostructure, like Lego bricks, and just put them together in a way that you get the properties that you want. Recently, it has been shown also, and it has generated a lot of interest, that if you twist them, so you put a small angle between two layers of a two-dimensional material, you get an emergent Moiré pattern. So you get a relatively large length scale from that. And that means that you can really generate completely new phases in graphene. So graphene itself behaves completely differently from twisted graphene. Another thing is that there are many quasi-two-dimensional materials, and cuprate superconductors are probably the most famous example, which are kind of layers where electron transport within the layer is very different from the vertical direction. And another thing that you can do is that if you have a two-dimensional material, then you really have an environment. This is a bit of a difference from a bulk material in 3D, where in the middle of the thing, you just have the material itself. So perfectly flat 2D material, you can put two different environments on it, and you can see that the material properties actually change. So here is the gap as a function of position here, that by putting dielectric materials on top of your single layer, you actually change the band gap or other properties of interest. I will show you two case studies that are kind of recent to kind of give you an update of what we've been doing. One of them is niobium disulfide, where we have charge density waves, and another one is niobium trichloride 8, where we have magnetism to connect to the topic of this session. So for the first one, niobium disulfide, the group in Cologne made STM experiments where they grew this TMDC monolayer on top of iridium with graphene as a spacer layer in between, and then did STM experiments. And at high temperature, you find a nice lattice like this. So this is just atomic lattice. When they lower the temperature, you find that you get something which has a different periodicity from the atomic lattice. So there is a periodic distortion that has a wavelength of roughly 3 interatomic distances, where basically what happens is that the atoms move and that then there's a reconstruction of the associated electronic structure. And in STM, you can look at this both below and above the Fermi level and really see how does the electronic structure change as a function of energy. We did then theoretical modeling for this, because here you can see that something has happened, but it's maybe difficult to understand exactly what has happened, what is the mechanism, and what is sort of the end result. So in this system, what's happening is that there are displacements of the niobium atoms, and there are several possible periodic displacements. I've shown 4 of them here. And what we did is to model how much energy gain you get from these displacements. So the point is that the atoms displace. This changes what the potential that the electrons feel. This changes the band structure of the electrons. And since some of the bands move downwards, this leads to an electronic energy gain. And this is the thing that stabilizes this phase transition. And it's kind of similar to the Jahn-Teller effect, which was mentioned in previous talks. Except that the Jahn-Teller effect, usually you think about molecules, where you have degenerate states that split up due to atomic displacements. Here it's about metals instead of molecules, but still displacements that lower the total energy. And what happens at that point is then also that instead of having a single nice band, you get splitting of the entire band structure into several side bands. Okay, that effect of charge density waves is already relatively well understood. What was interesting here is that in the experiment, they found that if they zoomed in to energies very close to the Fermi level, they found distinct, relatively symmetric peaks. So the dashed lines indicate where these features are. So they did STM in several spots and found always at the same energy peaks. And initially, we didn't really understand where these were coming from, because especially the fact that it's symmetric at that such low energy is something that was surprising to us. And what we believe is the resolution of this is that because there are several charge density wave modes that are close in energy, if you have gone into one of these modes, there are other modes which are still relatively close by. So you have phonons that connect you to these modes, and those phonons remain at low energy. So here are in purple, the energies of the phonon modes that connect one charge density wave state with another. And these are essentially at this 5 or 10 MeV scale. So we believe that what we see in the experiment is not just electronic structure, but actually the coupling of the electrons to the phonons. So really combined dynamics of the two particles. Then the second example, niobium trichloride 8. The bulk system has been known to be an insulator already since the 80s at least. But there's now recent interest in studying few layers or monolayers of the system. Part of this general trend, I think, that many systems that were known in the bulk nowadays we want to make also very thin. So here are some results, for example, from Delft, where they did thickness-dependent studies of electrical conductivity. And our goal was to give kind of a theoretical description of this material, what's happening and why is it happening. So this material looks like this. There is a lattice of niobium atoms in blue and chloride atoms around them. And if we actually look at the picture once more, the niobium atoms form a lattice like this that consists of triangles. So it's a bit like a Kagome lattice, but it's not perfectly a Kagome lattice because there are small and large triangles, as also drawn here in the sketch. And what that means is that you get a band structure that is a bit similar to a Kagome lattice, but because of the distortion, it has changed. So here is, if you had a perfect breeding Kagome lattice, you would have this band here. While in dashed, you would have if you had a Kagome lattice where all triangles are the same size. We did density functional theory calculations for this to really get kind of material specific results and got a band structure that looks like this. So there are 3 bands relatively close to the Fermi level, and one of them only actually that crosses the Fermi level. So if you see this, you would say, well, the system is a metal. There have now been RPES results, and they show this, not a metal. There's clearly no spectral weight at 0. So what explains this? Well, the thing is that essentially these 3 bands correspond to states which are living on these 3 niobium atoms. And if we look at the lowest one, it's an orbital that basically looks like this. It's like a molecular orbital on this trimer. And what you can also see is that the bandwidth of this band is very small. So that means that the kinetic energy of these electrons is very low. They're really just staying on the trimer and not really moving to the next trimer. And that also means that if you look at the computation between kinetic energy and potential energy, since the kinetic energy is so small, actually potential energy wins out. So interactions between electrons are strong, and you should take them into account beyond the DFT level. Okay, here's once more the picture from the experiments. So what we believe is that this is something that is what is called a Mott band or Hubbard band. So you have these electrons moving around. If there's one electron on every side, and if they strongly repel each other, then they get stuck like a traffic jam. There's one on every side that cannot move. So if you take into account the fact that these are interacting particles, not just non-interacting particles, what you get is that it takes a lot of energy to actually move them. And this fact that it takes a lot of energy is what is the gap in the spectrum, in the alpha spectrum. What you also get if you have localized electrons is that every electron has spin 1/2. So there are localized moments, and the localized moments couple together, and the localized moments can order magnetically. And typically they want to order antiparamagnetically in cases like this. So what we did is that we took also into account this interaction, and we got a spectrum that looks like this. And this is the APES spectrum. I've tried to make the scales line up. You see that it's not perfect here. This thing is a bit higher up than this. The disadvantage, I think, in APES is that we don't really see the upper half. So we would like to know how big is the difference between the this band and this band, but APES doesn't tell us this. What APES can tell us is the renormalization of the band. So you see that these have a small dispersion, and this also gets interaction renormalized. And this is probably the best way to see how important correlation effects are in a system like this. Finally, we then looked at magnetism, and we did relatively crude methods, I should say. We've seen much better modeling of magnetism. But what we found here is that energetically it's favorable to align the spins at 120-degree angles with one spin on every red triangle. So every one of the molecular trimers has spin 1/2, and they orient like this. With that, I would like to acknowledge my collaborators. So the people in Cologne who did the experiments, the people in Bremen and Hamburg who did also the theory for MBS2, and the people in Nijmegen who I collaborated with on the MB3 CL8 theory. So in conclusion, I think 2D materials are kind of interesting. They're really different from 3D. They have interesting phase transitions and also possibilities to manipulate them by stacking, by twisting, by substrates and other environments. And that experiment and theory should go hand in hand for the description and understanding of this kind of material. Thank you.